Hello friends, today I would like to explain something about compound interest and the Euler's number. So many of you are familiar with compound interest, the idea of it, but how do we actually compute it? Let's check. So first of all, if we have, let's say, we start with some amount of money, KO, and we are having 4% of interest rate. So what is the amount of money we are going to have 1 year after? And so basically, what is K1? Well, as you can see, K1, this is the total KO plus 4%, which is 0.04 of KO. And now, as you can see, I can think of it as 1 times KO. I can take, using the distributive law backwards, I can take KO out of the parentheses, which gives me 1 plus 0.04 times KO, which is 1.04 KO. So this is the value K1 that we're going to have after a year. What will happen with K2? Well, K2, assuming we're not changing the interest rate, this is K1 plus 4% of K1, and we basically have 1 times K1 again. So as you can see, we once again take K1 out of the parentheses, and we're going to have 1 plus 0.04 times K1, but now we also know, so this is 1.04 K1, we also know that K1 is 1.4 KO, so that means we are substituting instead of K1 1.04 KO, and we're going to have 1.04 times 1.04 KO, which gives us 1.04 squared times KO. All right, so the idea is clear. The further we go, the higher the exponents would be. So that means, as you can see, there is a correspondence between 2 in an indicator and 2 in the power. So Kn is going to be 1.04 to the power of n times KO. So that's the story. This is the idea of compound interest. If you're bringing your money to the bank and if you get 4% a year, so there are so many questions like what is how long would it take in order for KO in order to double, to triple, and many other questions. We solve them easily with logarithms. But now let's think what will happen if we're basically thinking of 1 year, but we have to wait the total year for the money we get. Like, imagine this is the 2nd of January, you're bringing your money to the bank, and you're coming on the 2nd of January in a year, and you're getting your whole money back, assuming the bank is not bankrupt, and you are getting 4% more. So the thing is, but the money is actually, well, being used by the bank as a total year, and well, you are not actually using it by yourself. So maybe you ask, what will happen if you are asking the bank to pay out after 6 months, not to wait for a year? Then you're going to gain a bit of money, and then for the second half of a year, you are putting the total KO plus the money you gained, and this money is going to be invested for the second half of a year. So at the end of the second half, you're going to get a bit more. Maybe this is the case. So let's have a look what will happen. So this is the story. We have, let's say, K1 star is going to be, well, I'm dividing 4% by 2 because I'm doing it twice in a year, so I'm still having KO. What I'm doing now, I'm having 1 plus, instead of 4%, we're adding 4% divided by 2. So what will be the amount of money we're going to get after half of a year? So this is, as you can see, 1.02 KO. So slightly more than KO, but we are going to get it after 6 months. So what will be K1 double star? Well, you see, in the second half of a year, the money that I start with is not KO anymore. This is KO times 1.02. So what we're going to get is KO times 1.02 times, well, this is the same interest rate, so 0.04 divided by 2, and this is 1.02 again. So this is KO times 1.02 squared. And if you plug it in your calculator, you're going to see, or you compute it on your own, you will see this is 1.0404 KO. So slightly bigger than 1.04 we're normally would getting. But then you say, well, just a tiny bit bigger, so why bother? Well, we don't know what KO would be. Imagine KO is $5 billion. So for 10,000s could be a huge amount of money. By the way, you're getting it for free. If the bank is if your bank is confirming this computation, why not? So the idea is clear. If we subdivide the interval of 1 year into smaller pieces, we are going to get always a bit more money back. So this is a very good idea maybe to start with. So what will be happening if we divide it into 4 or 6 or into 12 pieces? Well, you see, basically what we were doing here, we were dividing the interest rate by the number of the divisions, and then we take this factor to the power of which is also the number of divisions. So basically what we're having is, let's say, K1 and then let's say 6 stars, so subdivision into 6 intervals, would be 1 plus 4% divided by 6 to the power of 6. So that's the story. All right. And this value times KO. And this value is going to be bigger and bigger all the time through. Okay. So the question is it going to rise forever? Or is it a limit? This is the very important question. And the answer is there is a limit. And in the medieval ages, 4% wasn't a thing. The interest rate was 100%. So that means if we are computing an interest rate with 100%, this value is going to be slightly different. We're going to have 1 plus 1, because it's 100%, divided by, well, let's say we divide it into n parts, to the power of n. This is the factor we're going to work with in order to compute the money after a year, subdivided into n pieces. And the higher n, the bigger the amount of money we're going to get back, but the speed of increase is going to be to get smaller and smaller. So the value 1 plus 1 divided by n to the power of n is still increasing. It's increasing forever, but it's bounded from above. We call it this way at the university. So at some point it's not increasing any, or they increase it that small, we can actually neglect it. We say, well, we don't see anything. And this, my friends, is the definition of the very important number in mathematics, and this is the Euler's number. So the Euler's number is a limit by n running towards infinity of 1 plus 1 divided by n to the power of n. And this is approximately 2.71828, 1828, 45, 90, 45, 23, 53, 60, and so on. It's a never-ending number. It's so-called irrational number as square root of 3 or square root of 2. You can check my channel again. So it's pretty easy to memorize this. 1820, so 2.7, you should be able to memorize this at least. But 1828, this is the birth year of Jules Verne, one of the, well, most famous French writers. I loved his book as I was a child, so twice his birth year. 45 is a half of a right angle. 90 degrees Then 45, I used to play basketball professionally, so it's Michael Jordan right here. Then you see 2 plus 3 giving you 5 and 360 degrees. So it's kind of way to memorize. You don't have to memorize actually up till 6 or 7 digits. It's absolutely fine. All right. So I hope you enjoyed it. I hope you learned something new. If you have questions, let me know in the comments and have a good day. In the next video, I would like to explain about some properties of the Euler's function e to the power of x. We'll talk about tangent lines and we'll talk about maybe derivatives as well. Okay, so see you guys. Stay tuned. Bye bye.